Okay, welcome to the NUPOC video study guide number 71. Let's keep going with some more dynamics problems for now. This one is actually, if you look in the second study guide from the Navy in the physics section, this actually comes up as question 12. The only difference is in that question they're actually doing it in feet, and we're just going to go ahead and do it in meters here, and it actually kind of works out a little bit easier. It's easier to kind of do the math in your head and whatnot, and just move through it faster if you're doing it in meters. So anyways, we'll just go ahead and start. So what they give you here is this projectile motion problem where we have some projectile, like let's say a ball, right? And it starts here at x equals 0 and y equals 0, and it flies up along this path, and it lands somewhere over here, which is 300 meters away, and it takes 4 seconds to travel that entire distance, right? And what they want to know is what's the maximum height that the projectile has reached. At first, you can kind of think of it almost as like, like a trig problem where we have two components, right? We have our x component, right? We have some velocity in the x direction, so I'll call that v sub x. In fact, we'll call it v0 sub x for our initial velocity in the x direction. And we have some initial velocity in the y direction, right? v0 sub y. Right? And these are both components of whatever our initial velocity is, which is tangent to this path here, right at the instant where the object starts moving, right? And that is v0. And of course, these are all vectors, right? So if we kind of use our trig and break this down into different components, it makes the problem a lot easier. So we're interested in h max, which is really our y max, right? So we're really interested in the y displacement, or the distance in the y direction that the projectile travels. But we're not given what the initial velocity is, right? So we're only given the total x distance and the total time. So we need to figure out some other equations instead of just using, we might be tempted to use something like, we would say maybe y max, right, which is h max, equals, we can use our motion equation, right, where we have 1/2 g, because we assume our acceleration is only in the minus y hat direction, and that's g, right, force of gravity, or the acceleration due to gravity, t squared plus v0 y t plus y0, and of course y0 is just 0, right? But we really don't know what v0y is. We don't know what it is as a number, right? So it'd be kind of hard to solve for y max. So we can use this as a starting point, but instead of going directly for y max, let's start with a y position that we do know. We know y at the final time here, right? This would be y at 2 seconds, right, because it's halfway through the flight. But we don't know exactly what y is, and we don't know what v0y is. So let's go ahead and use this same equation, but let's apply it to this point out here. So this would be y final, and we know what that is. We know y final is the same as y initial, which is 0. So we can say that 0 equals 1/2 g t squared. Now in this case t is 4. We know it took 4 seconds to get there, so we'll say 4 squared, right, plus v0yt, and we don't know what v0y is itself, but we do know its relationship to v0, so we're going to use v0 to sort of link v0y and v0x. So we know that excuse me, v0y, right, if this is our angle theta, right, the angle between the xz plane and where the direction that the projectile takes off, and if this is our angle theta, then we know that v0y is just v0 sine theta, right? and y0 is of course 0, and this is, we have t here, so that's 4, right? So when we go ahead and do all this out, we find v0 equals 19.6 meters per second, right? Because this is meters per second squared, g, right? It's minus 9.8, right? G equals minus 9.8 meters per second squared, and this is of course a second squared, right? So we end up with meters here, and we end up with of course with seconds here. So when we divide this sine theta times 4 seconds over to the other side, we'll get v0, right? v0 equals 19.6 meters per second over sine theta, right? Okay. Now let's go ahead and use v0. Let's use another equation to also solve for v0, and then we can set those two expressions for v0 equal to each other, and so we can sort of link between v0x and v0y using just v0 here. So let's use our equation of motion in the x direction. This was our equation of motion in the y direction, so let's look at the x direction. Well, there's no acceleration in the x direction, right? So what we can simply say is that x final, which is 300 meters, so we can say 300 equals v0x, which is simply v0 cosine theta, right, times t, right, which is 4 seconds. It also takes 4 seconds to reach this final position. So we can say that v0 equals 300 over 4 cosine theta meters per second, right? So when we set these two equal, right, v0 equals this, and it also equals this, so we can say then that 19.6 meters per second over sine theta equals 300 over 4 cosine theta meters per second, right? And when we set those two equal, we find that we have 19.6 meters per second, right, over 75 meters per second equals tan theta. After we do a little bit of algebra, right, we move the sine up on top of the cosine, right, and that gives us our tan theta on one side of the equation, and the other side is just the rest of the expression, all the numbers here, right? Okay, so this is also equal to about 0.26, and when we take the arctan of 0.26, we find that theta, right, equals about 14.6 degrees. Okay. So now we can plug this theta, right, back into our v0 expression, either one, it doesn't matter, and we can find out what our v0 actually is. When we do that, we find that v0, right, if I plug in 14.6 degrees for theta here, let's say, we find that v0 equals about 77.5 meters per second. Okay. And now if we know v0, right, and we know theta, right, then we know v0y, right? It's just v0 times sine of theta, or sine of 14.6 degrees. So now we can go ahead and use that and just go right back to our what we initially wanted to do, basically, which was use this equation of motion, right, to solve for the y displacement at 2 seconds, right? So we can actually say y max, or I'll just go ahead and say h max, right, because that's what I labeled it on the diagram here. H max equals 1/2 g t squared, but this time it's going to be 2 seconds squared, right, because this is halfway through its flight, plus v0yt, right, well that's just 77.5, right, meters per second, which is v0, times sine of 14.6 degrees times t, which is again 2 seconds. And when we do this all out, this ends up equaling, this first term is minus 19.6 meters, the second term is plus 39.07 meters, roughly, and that ends up giving us 19.4 meters. So our H max, the maximum height that the projectile reaches, is 19.4 meters. And if you check that with the solution that they provide for this problem here, question 12 in the physics section of guide 2, I believe that should match their answer as well.